In chapter 14, we will touch upon analysis methodology for stratified samples. So in chapter 13, we discussed the principle of stratification. We do recall from chapter 13 several things, but most importantly that there are two different rationales, goals to do stratification. One is to increase the overall precision, but we have to make sure we do it well. And two, because we want to make statements, inferential statements about the strata separately, individually, to compare them or to put the results next to each other. But no matter how we do it, at the end of the day, the question is, how do we translate our design into an estimation strategy? How can we take that into account? So, population quantities and estimators, what do we have? Well, what is the general principles? The general principle is you estimate a quantity, that can be an auxiliary quantity, but let's now say we estimate in every stratum separately, and then we combine all of that into a single overall result. So, let's say the outcome y takes values y, h, I. So that is the outcome, the body mass index, for example, for a member of the population I who belongs to stratum H. YH is the stratum total. And then YH bar is the average within stratum. And that's not theory or anything like that, it's notation. Huh? So what is the population total? You take the stratum specific totals, and you sum them all, and then you can introduce the definition of the stratum specific total. So you sum everything within a stratum, and then you sum over all strata. Okay. So the population total is the unweighted sum of all members of the population, but taking into account their stratum nature. For the population average, it's a bit more complicated. So, well, what is the average within a stratum? The average within a stratum is the total within a stratum divided by the number of people in the stratum. So, the total within the stratum divided by the number of people within the stratum. Now, what is the population average? The population average overall is the population sum divided by n. So, let's do that. But the population sum we have, if we go back, we have that from the previous page. That's the population total. Okay. So we fill that in here, the population total, and we are then going to see what that now really means. So what is the population total? This is the population total. It's a total within a stratum which we sum over all the strata. Or, indeed, taking the equation from the previous page, that's what we get. Okay, so y hat is 1 over n divided by this number. Now, if we look at that in a little more detail, we can say, well, wait a minute. If I look at the total, I can also say it's actually this quantity summed over the strata, so the stratum specific total, but here I have this funny insertion of NH divided by NH. Why do I do that? Well, definitely it's not wrong. Huh? It is actually like this quantity here, but where I make that funny insertion. Okay. Now, what I'm going to do is I'm going to single out this thing and put it in a parenthesis. And then on the outer side remains the sum of NH divided by n, because I can just as well bring the n inside, right? So what I'm looking at now is this, but there is a 1 over n in front. I can bring that inside. So, what is here now between parentheses is nothing but the average in stratum H. So I can denote it by y bar H. In other words, what I get at the end of the day is the sum of all of the stratum-specific averages multiplied by a weight. And again, in yet other words, if I go back one page, what I see here is the total of the population is the unweighted sum of the totals within the strata. The average of the population, though, is the weighted sum of the averages within the strata. And there's some intuition behind it. If I take the average of Flanders, Brussels, and Wallonia, and I simply average them, you're going to say, hey, wait a minute, Brussels is much smaller than Flanders. You cannot simply average them. No, you cannot, because you need weights for that. But if I have the total income of Flanders, Brussels, and Wallonia, I can simply sum them, because indeed, the total income from Flanders plus the total income from Wallonia plus the total income from Brussels, that is, of course, the population total. Each one of those three totals will be the sum of a different number of people, and therefore will be bigger or smaller depending on whether it's a bigger or a smaller region. But in the average, that size information is lost. So if I just look at three averages, I cannot say which comes from a larger, a smaller, or a medium-sized region, and therefore it's not unnatural that these weights pop up. The smaller a region, the smaller the weight will be, the less it will contribute to the overall average. Okay, and what are the weights? The weights are nothing but the fraction of the population that belongs to a stratum. Evidently, and you can quickly check that, do it, evidently the sum of the weights is equal to 1, which suggests actually a slight rewrite. I can write it in this way and say the average of the population is the classical, follows the classical weighted average formula from the stratum-specific averages. And now the WHs, yeah, they can still be NH divided by N, and then you will see that the denominator here is actually equal to 1. But you can just as well say, if you forget everything above, say this is now the formula, and as long as the WHs are proportional to the size, it's fine. So I can write them as NH. Okay, now they don't sum anymore to 1, they sum to n. But I will be dividing by n in numerator and denominator, and it all cancels. So the advantage of this formula is it automatically self-corrects. It doesn't blow up or deflate according to whether I use a numerator in the weights, whether the weights sum to 1 or to 10 million or to a billion or to 0.05. I don't care, because this is self-correcting in that sense. Okay, now recall, observe that so far we have been discussing population quantities. That's all nice and well, but now it comes to estimation based on a sample. How do I do that? Well, YH, but now lowercase, would be the total across all subjects that belong to stratum H. So, for example, the 3,000 people in Brussels, or the 3,500 in Wallonia. So what is the stratum-specific total in its estimate? It's not a sum of the population, of the sample units, it's the sum of the sample units inflated by the inverse fraction. Okay, so once I have that for every stratum, you simply add it all up and you get the estimate for the entire country. For the averages, well, the average in a stratum is the total in a stratum divided by the number of people that you have in your sample from that stratum. So what is the estimate for the population average? That is the estimated total divided by n, and you can pull in the estimated total by saying it's the sum of the stratum-specific totals, and that's it. Or you can write it in terms of averages, and also here, if you write the average as a combination of averages, it's a weighted combination, it's a weighted sum, whereas for the total, it's an unweighted sum here. So I should go to the bottom rather. The estimated population total is the sum, the unweighted sum of the estimated stratum totals. The estimated population average is a weighted sum of the estimated stratum-specific averages, in line with what we did at the population. And then for ratios, well, for ratios you can do your estimation for y, for x, and then you divide by it. But wait a minute, this is now the ratio. For example, let's imagine you're interested in the ratio between systolic and diastolic blood pressure. Or you're interested in whatever other ratio. Well, here you're doing this at the level of the stratum. But I'm interested in the ratio for the population. What can I do right now? I can actually calculate y hat, or estimate y hat, x hat, or y bar and x bar first, and then calculate the ratio. Or I can calculate, like we did here, all the ratios and try to combine them. So these are two different options. RH is okay. I now have ratios stratum by stratum. Or I can calculate a ratio here by first summing across strata in the numerator, summing across strata in the denominator, and then calculating the ratio. So, what I can do with these guys is benchmark estimation. One benchmark would be, okay, I'll calculate a benchmark total, I'll estimate a benchmark total for every stratum separately. So that is stratum specific. And then you combine them in the usual way, by just adding them all up, and you would get something like this. That is stratum by stratum. You do the exercise in every stratum separately. That gives you the benchmark corrected total for stratum H. And at the end of the day, you have your population level. Or you can go across strata. And that is, you first construct an overall estimator for the ratio, and then you forget about stratification at that point, and you do the correction immediately at the population level. These two procedures, across stratum, which we discussed now, and stratum by stratum, which we considered a moment ago, are not identical. If all goes well, they will produce more or less the same result if you have a large sample and a large population and everything works well, but they don't have to be the same, that's for sure. It looks like the stratum-specific benchmark estimator is using more information, more subtle. You do it stratum by stratum, but wait. If your sample size is considerable, it may still be that it's considerable overall, but not necessarily in every stratum separately. So if you do a correction based on not such a large sample, it may still be very variable. And therefore, for relatively small, medium-sized to small samples, actually across stratum may do a little better than stratum by stratum. Okay, so that's what I just said. If your NHs are very variable or very small, be careful. You may want to borrow strength by doing things across strata indeed. Okay, variances. Point estimates, either directly after stratification or with on top of that benchmark estimation, because don't forget, benchmark estimation is something that we do after the first estimator has been calculated, which is the one for the stratum. Okay. We need to calculate precision. Okay. So we need the population variance, like always. All tables have so far shown a population variance, and then the variance of the estimator that derives from it. And once I have that in calculable, we say, form, we indicate how we can estimate it from data. Well, we have to do something similar here, of course. Okay, so the population variance now takes a form very similar to what we have seen before. think of benchmark estimator. For benchmark estimators, the population variance is the same except we replace y bar by rx bar. Or rxi. In the simple random sampling, we simply compare with the overall average. But now we say, wait a minute, we do things here stratum by stratum. So we calculate the variance not overall and once, we calculate it h times, capital H, as many times as we have strata. So this is the stratum-specific version of the population variance. And yes, that's the estimated form where you rely simply on the units that you have in your sample. So for the total, you apply the same formula we had before. By before, I mean with simple random sampling, but then for every stratum separately. So that gives us the total, the variance of the total estimated for stratum H, and the same for the average, and then yet the same for the estimated quantity. So are we done? No, we're not done. This is only stratum level. So on this page, we see what we have to do stratum by stratum. Next, we move up and we say, what does this now mean for the population? Well, the population variance is the sum of the stratum-specific variances. The total, for the total, we have the sum of the stratum-specific variances. For the average, guess what? We have a weighted sum of the stratum-specific variances, but the weights now, because of the quadratic nature of a variance, are not the original weights, they're actually the squares of the original weights. Okay, and now we can go further and say, when benchmark estimation is compared with stratification, we also can work out the variances, and then the population variance is going to look like the benchmark variance we had before, but with h's on top of that, because this is also stratum specific. We have similar quantities for when we deal with the across stratum estimator, etc. And if we look at those expressions, they all of a sudden start to look many, and it's a bit confusing, but the thing is, no. You just think about the design. What have you been doing? Benchmark estimation, well, then go back to the previous part. Stratification, oh, you're good. You can go back a few pages where we had the stratum level quantities and then eventually the population level quantities. The two combined, stratification and benchmark estimation, then this table applies, and of course in practice from a set of data, this is what you use. So there's no point in learning this by heart. There is point in understanding what it now is, what we are doing. So the variability is reduced by the fact that we can use individual level prediction and we can do that stratum specific. And therefore we refine things in two ways, and if we do well, we will actually have reduced the variability quite a lot. But the most important thing is know that for every situation, and here it includes the combination of two techniques, stratified sampling and analysis is combined with benchmark estimation. Okay, the formulas follow suit, they can be calculated, and it's important that I use the correct ones because they will allow me to save on precision, of course. Okay, now let's look at an example. We have done this example as a running example every time we add a little bit of information. We have done simple random sampling, systematic sampling, benchmark estimation, now stratification. So the artificial population with just the 4 units, what have we done already? Well, we have looked at the variance under simple random sampling with and without replacement. And recall that under systematic sampling, we brought in this somewhat confusing but important concept of correlation. If you apply a good, and by good I mean a precise sampling mechanism, it will make your samples heterogeneous. So you avoid that everybody has a high body mass index and everybody has a low body mass index. No, you spread it out relatively evenly across the population. That means some large values are compensated by some small values, and that corresponds to a large negative intra-sample correlation. That's what we have here. So that's why for simple random sampling without replacement, with a somewhat negative correlation, you're better off in terms of variance than with replacement where the correlation is 0. And why again is the correlation 0 if you sample with replacement? Well, you take a unit, you place it back, and that unit could come out again. So it's completely memoryless. If you sample without replacement, there is a little bit of a memory. What has come out cannot come out again. So new values will therefore be at least a little bit different from existing values because they cannot be the same anymore. They have been taken away. In systematic sampling, we see that we had this, we recall that we had this because of small population size, very peculiar list where the correlation is -1. Don't expect that to happen in practice, but it's because it's an artificial example. One list has a negative correlation even smaller than simple random sampling without replacement, which is good. The other list has increased the correlation to a positive value, and that's not very good. Well, if we stratify with one stratifying variable, we have a correlation of -0.80, and that's the smallest value, or rather the largest value in absolute value, but negative, so that is a very good mechanism. The one where we go to 0, that's not very good because we sample without replacement, but we get a variance that corresponds to simple random sampling with replacement. So we could have done better. That second stratification, that second stratifying variable did not work very well. Okay. All right. So stratification, if done well, would typically decrease precision. And that is a source of a lot of variability. Some people say it always, it should decrease variability, increase precision. Some people say stratification, if done well, leads to smaller variances, better precision. In the worst case, it doesn't do anything, but it cannot make things worse. Well, it can. We just saw that because here the correlation is 0, which is less than the default simple random sampling without replacement of -0.33. We don't do so well. So it's possible to do worse than doing nothing but simple random sampling. And to understand that, let's look at it in a bit more detail. So we construct a simple artificial data set where we say the 4 units that we have, the 4 observations, are stratified into the stratum consisting of 1, 2, and 3, 4. 1, 2, 3, 4, you can also do it there. But there is also a second stratification, and that would bring together 1, 4, and 2, 3. That's another stratification. Okay, that's nothing but a stratifying information. And now what we're going to do is we're going to calculate the average. We're going to model the average, but for every one of the strata separately. Well, first what we do is we calculate a simple linear model, a simple average actually, based on no other information than that I'm using the entire population. In the second case, I let the average depend on the stratum. So effectively, I calculate a mean in every stratum separately. Okay. So for the non-stratified case, I find corrected variability of 25. Don't look at p-values and things. We're talking about a population. That's not important. Or an uncorrected total of 30, which means the variance decomposition is such that the model, i.e. the mean, there's nothing else, takes away 25 sums of squares and the remaining error is 5. So the uncorrected total is the variation around 0, but that's not very interesting. So the total error variance, in other words, is 5. Okay. If I do the good stratification, I see that by taking the stratum into account, the total of 5 is split further in 4 for the model and 1 for the error now. What does that mean? Well, it means that the total error is split in a portion that goes to the model, i.e. the stratum. So the variability between the units, 5. 4 of those 5, so 80% of the variability can be allocated to the stratum means that are different. So I have 2 units here, I'm exaggerating a bit, 2 units there. Here is the overall mean, but really the most important discrepancy is between the stratum specific means, the bullets here. The variability within the stratum is really small, that's only 20% of the variability, that's the one there. Okay. If I go for the bad stratification, there I expect the reverse, but how is that going to be? How can the sums of squares be decomposed in, let's say, 7 and minus 2? It doesn't work, and that's why it looks at 0. And that's where people get the idea from. Even a bad stratification doesn't do anything. It keeps the variability intact, but it doesn't increase it. Wrong. But the thing is, in this way, the way we are looking at it now, we can see what a good stratification does. It takes the total variability of 5 and decomposes it in 80% that goes to the stratum, which we take away by stratifying. That's great news, right? We reduce the variability with a factor 5, but it's still not clear what happens with the bad stratifying variable. So, therefore, we are going to consider a different model and say, okay, how does an observation come into being? Well, an observation, Yij, where I is, guess what, the stratum now, and j is the subject within the stratum, that observation is made up of the overall population mean. That's where we start. But of course, not everybody is equal to the population mean, because no, this person belongs to stratum I, and the mean of that stratum is not mu, it's mu plus bi. We can always write it that way. If the mean is 7, but the mean in stratum number 1 is 8, b is 1. If the mean is 7, but the mean in stratum number 1 is equal to 3, well, then the correction is minus 4, and that goes into the b. But still, not everybody is equal to the average in their stratum. No, people are people and they're individuals. So the epsilon is the individual component that makes everybody a little or a lot different from the stratum-specific mean. Okay. From stratum to stratum we have variability. Not every stratum mean is the same. Flanders, Brussels, Wallonia, they're a little different. So therefore it's useful to put even a distribution on that, just for the sake of argument. So let's say they are normally distributed. Tau square is, if tau square is very large, it means strata really are very different. If tau square is equal to 0, it means, on average, strata are all the same. Epsilon. If sigma square is large, it means that even 2 people from the same stratum will be very different. If sigma square is small, it means, yeah, people are from the same stratum and therefore they're similar. So it all has an interpretation. This is the same as the ANOVA model, but formulated slightly more flexibly, and exactly the flexibility that we need. So we can fit that in SAS with prop mixed, but also in SPSS, in R, that can be done. And we'll talk about more in the complex design-based analysis. All right, so let's first do the non-stratified case. We then find the residual variance to be 1.25. If you multiply that by 4, you're back to the 5, because this is an average. Now, if you do this for the first stratification, you see, for the first stratification, we see not y is equal to stratum, but we see that stratum is considered a random effect, as we do here. And now we get stratum-specific variability tau square to be 0.75, residual variability, sigma square, to be 0.5. So, the sum of the two, 1.25, is the same as here, but now decomposed into something in terms of variability that belongs to stratum and something that belongs to the subject. Okay. With a bad stratification, hey, it looks like we haven't made any progress. We feel that somehow the stratification has made it worse. And that actually showed from the result. But we still have a 0 here. So we don't get anywhere. We seem to not be able to capture it. The thing is that there is actually a negative value hidden behind the stratum too. But in the basic use of these models, it's not allowed. But we can make it happen by putting in the no bound option that says, okay, if a stratum is worse, tell me. That's what I'm now saying to the program. And look at that. The residual variability has increased because strata actually are not dissimilar. They're actually very similar. They're overlapping, which means by picking people from different strata, I tend to end up with homogeneous samples as possible. If they're overlapping, it's possible that I get a small value from stratum 1 and a small value of stratum 2, and they're very, very similar. So by doing it in this way, actually, stratification makes heterogeneous samples difficult, if not impossible, completely the opposite action, and that shows through a negative variance component. It throws something in, that means it throws in variability rather than removing. And yeah, the variance was 1.25. You throw in, because that's what the negative sign says here, 1.25, it gets to 2.5. So the variability has increased. Okay, let's see whether we get this by doing it again, same exercise, but now for survey town. So there are two stratifications, right? The one based on X and the one based on Z. The X one is the good one, the Z one is the usually suspected to be less good one. Okay, so these are all the possible samples that we can take up until at the very end. 4 by 4 is 16, so we have 32 observations, it seems. That's not really what it is, because this is not really a sample or the population even. No, it's all possible samples that we are looking at here, just to see how the sampling mechanism behaves by looking at all possible samples. And we do the same in the Z case. Okay, what are the correlations now? The correlations are with the X list minus 0.76, which is great. If it's very negative, that's a good thing. The within sample correlation with Z, it's not so great, but it's still negative, which means we haven't really made it too much worse. It's still reasonably good. So we see that listed here, all the various cases. Simple random sampling with replacement 168, without 144. For the two lists that we have now added, we're down to 40. And yes, the 168 is still coming down a little bit to 160, but no, it's bigger than what we would get simple random sampling without replacement. So the Z list is not a total disaster, but it's not something to recommend. It's extra work, and you still do worse than simple random sampling without replacement. Whereas list X, systematic sampling, produced 80, and list Z, which we thought also would be very bad, still produced up to now the best result, but that's more a coincidence than anything else. Okay. Let's now do the same as before, look at the variance decomposition. So here we look not at all, here to get the correlation, we consider every possible sample, which we can also only do in a small textbook example. To get the idea of the variance decomposition, to get an idea about the variance decomposition, we take all units, but we simply indicate what stratum they belong to. So this is the population with its stratifying structure. Okay, for the X stratum, let's see what we get. We find, if there is no stratification, a variance of 5.25. With stratification X, the stratum takes out 3.58 and leaves only 1.66. But stratification Z, recall, which was slightly worse than simple random sampling without replacement, brings it down, brings it up rather to 6.767 because it throws in a little bit of additional variability. It didn't double it like in the previous case, but still it's not perfect. Okay, so what is the good news? What is a good stratifying variable? When the strata are homogeneous, which means people from the same stratum are more similar than people from different strata. If strata are homogeneous and I take people from different strata, I make the sample heterogeneous, and that's exactly what I like, beneficial. If you take all the words in red in the top half of this slide for list X and you replace it by their counterparts in the bottom of the slide, homogeneous becomes heterogeneous and vice versa, decrease becomes increase, good becomes bad or beneficial becomes detrimental, you have what happens with list Z, and this is what happens with list X. So, what is the lesson learned? Stratification, if we do it for precision increase, it can work if your strata are sensible and strata are homogeneous relative to the survey variable of interest. But that doesn't always work. And we have to work a bit. We have to work hard to find that out, to get that out of data, but it's possible. And for that we had to look into these mixed models, take my population, stratify it, and then calculate the variability within strata and between strata. And sometimes we see that the within stratum variability is larger than the overall variability, and that's only because some negative variance components are there. By stratifying, the way to interpret that is by stratification, we have made the strata less homogeneous than the population. The strata are too scattered. They're not homogeneous groups, no. And as a result, we may actually force ourselves to samples that are too homogeneous if we are unfortunate, and that actually leads to decreasing precision. It's a bit of a subtle message, but we should think about it in this way. Okay. And then combining benchmark estimation with stratification. Here, where have we done that before? We have done that before when we were discussing the estimators, of course. So let's look at what happens. We do benchmark estimation, but no stratification. We do benchmark estimation in the across stratum fashion, so one correction and that's it. And we do it stratum by stratum. So the benchmark, it's all benchmark estimation. The whole slide is benchmark estimation, all three columns. But stratification is done, no. And then when stratification is done, we do the benchmark estimation across all strata, and we do it in a stratum by stratum fashion. You see the bias. If you do benchmark estimation like that, there is a small bias, smaller with a cross method, but bigger stratum by stratum. And again, even though we think that a correction stratum by stratum is more refined, don't forget, strata may be very thin, very sparse. It may therefore all be very imprecise, and it may create more trouble than it actually solves. Okay, we have the range and then the variance. We have a small decrease relative to the 1.85, and we shouldn't judge that as being irrelevant. Well, don't forget that if you don't do stratification and you don't do benchmark estimation, and what is that? Simple random sampling, we get a variance of 144. So we bring that back by simply doing benchmark estimation to 185. benchmark estimation with stratification 1.5, but no, if you do the benchmark estimation stratum by stratum, it's not a nightmare, it's not terrible, but you do bring the variance up. And that's a message to keep in mind. Stratum by stratum benchmark estimation, well, it may be asking too much from the data. We do too many corrections for the data that we have available. Okay. Good. Now, what we have done is we have used a variable x, for example, for stratification, and we've used it for benchmark estimation. That's perfectly possible, but it's also possible to use different variables for stratification and for benchmark estimation. That's not necessarily, it doesn't necessarily need to be one and the same thing. Okay. All right, that's where we're going to leave it for now. And then in the next section, 14.6, we will apply it once more, but then in the realistic setting of the Belgian Health Interview Survey, where we will see what can be done with standard software.